In this video, we talked about transfer learning. Usually, training a very large deep neural network from scratch is very much computationally expensive. What you can do is that you can try to find an existing neural network model that was used for a similar task, and then you reuse lower layers of the network. This is called transfer learning. The advantage of this approach is that it speeds up training considerably. Also requires much less training data. Typically, you should replace the output layer of the original model. This is because the output layer is not useful for the new task. Also, it doesn't have the right number of outputs for the new task. Considering hidden layers, the lower layers in the structure are more useful than upper hidden layers. This is because the lower layers learn low-level features, while upper layers learn high-level features. And the high-level features that are useful for the new task may be different significantly from the features that were useful for the original task. Let's look at an example which is on the right side. We have an existing deep neural network which was used for task A on the left, and another deep neural network which is used for a similar task B. The principle is that the more similar the tasks are, the more layers you want to reuse. If the tasks are very much similar, all the hidden layers may be kept, and we just need to replace the output layer. In this example, 3 lower hidden layers were kept, meaning we reuse the width. Now in the new model, on top of the reused layers, another hidden layer is created, and on top of it is the output layer. The widths in the hidden layer 1 and the hidden layer 2 are frozen, meaning their widths are kept fixed and untrainable. The widths in hidden layer 3 are tweaked a little bit, and the width in hidden layer 4 are trained during backpropagation. You may have a question, how many layers to reuse? So what we do is that we try freezing all the reused layers first, and then train the model and see how it performs. And then try unfreezing 1 or 2 layers on the top, so that backpropagation can tweak them and see if performance improves. The principle is that the more training data you have, the more layers you can unfreeze. Also, you may need to reduce the learning rate so that it would not change too much the already fine-tuned weights. In the case if the performance is not improved and you have just little training data, what you would try is to drop 1 or 2 hidden layers on the top and keep the remaining hidden layers frozen, and then train the model and see if the performance is improved. If it is, it gives the right number of layers for being reused. If you have more training data, plenty of training data, you can try tweaking the top hidden layers. Also try adding more hidden layers on the top. Now we talked about the situation if you don't have much labeled training data. Also, you have no model trained previously on a similar task for being reused. In such a case, you may consider unsupervised pre-training. With unsupervised pre-training, what you do is that you collect unlabeled training data, meaning the data that you don't have labels at all, and train the hidden layers one by one, starting with the lowest layer and then going up, adding more layers using something called restricted Boltzmann machines or autoencoders. In the example, you can see that we start with unlabeled data and we trained the first hidden layer. Then use output of the first hidden layer to train the second hidden layer. And then again use the output of the second hidden layer to train the third hidden layer. Once you're done with all the hidden layers, you put the output layer on the top of your structure and now fine-tune the network using the label data. Note that when you train the hidden layers one by one, you need to freeze all the previous trained layers. So when you train layer 2, layer 1 is frozen. When you train layer 3, all the layer 2 and layer 1 are frozen. When you get to the final step, you can unfreeze some pre-trained layers or maybe all of them so that you can use the label data and let byte propagation tweak their widths